Okay, hello everyone, let's go ahead and begin. Let's take a look at planes and distances. Now in this particular section, what we're going to do is we're going to try to determine what the algebraic expression is, or algebraic equation is, for a plane in three-dimensional space. Now before we get to that, I think what we need to do is we need to review a little bit more about the two-dimensional space, and then we can go ahead and extend to the three dimensions. So let's go ahead and take a look here. Here is our little two-dimensional plane, our x and y coordinate axis. Notice that we said that this was the I, the unit vector, in the direction of the x-axis, positive x-axis, j, which is the unit vector in the direction of the positive y-axis. Now what we said is that any particular coordinate can be represented by a vector in standard position, so long as we go ahead and find a linear combination of I and j vectors such that we come up with the particular coordinate that we have. So we said that the a times by the I vector plus the b times by the j vector is going to give us a linear combination of I and j vectors to give us the column vector AB, which represents a particular coordinate on the two-dimensional Cartesian coordinate plane. So what that means then is that every single point that we have on the Cartesian coordinate plane can be represented in this particular form. That's an important point when we go ahead and move to the three-dimensional case. Okay, let's do that right now. Now, notice that the origin is here. It's no longer there. The origin is here. And what we have is we have a plane that's out in space. So how do we go about determining what the particular equation will be to represent that plane? Now, again, it's all dealing with vectors. Now let's go ahead and take a look at what we have. Notice that when the two-dimensional plane here that I have a vector b and a vector c, and those are going to be my basis vectors. If I make any linear combination of b and c, I come up with a vector v, and that means that I have all the points on the plane, which is similar to what we were talking about up there. So then the key then is that if we want to go ahead and start from here, this is where the origin is. In order for me to be able to get to any point that's on the plane, which is this resulting vector, then I need to make sure that I actually find a point on the plane first, and then go ahead and add the linear combination of b and c. So what that means then is that the resultant vector, which is actually a point from the origin, a vector which starts at the origin and ends at a point on the plane, has to actually get to the plane first, so that means a vector to any point on the plane, and then we need to go ahead and add the v vector, which is a linear combination of the b vectors and the c vectors. Okay, and so this is what we come up with. We come up with the resultant vector is going to be equal to OA, which is any point on the plane. A is any point on the plane, so this is the position vector, we call that the position vector, plus the linear combination of vectors that are already in the plane b and c. And so this then will go ahead and give us an accurate representation of any plane that we have. So notice that the thing that we have to recognize is that S and T are the parameters of the basis vectors for the plane. Okay, and let's go ahead and take a look at this form then. Now what we're going to do is we're going to go ahead and rewrite this in exactly the same form. It's just that R, which is our resultant, is any point that is on the plane, which is represented by x, y, and z, is going to be equal to the column vector of any point that is actually going to be on the plane, okay, plus S times it by the v vector, plus t times it by the c vector. And I'm just writing this in column form. So you can either use this form right here, or that form right there, and those would be the parametric forms of the plane. Now let's go ahead and take a look at an example. So say for example if A is 1, 2, 3, B is 3, 5, 6, and C is 7, 2, and 8. Okay, now what do we have to find? We have to find out this particular vector from O to A. Well, that's very simple because we know that A is 1, 2, 3, so O to A is 1, 2, 3. Then we need to go ahead and find out what AB is in order to find out what the B vector is. So that means that if I go ahead and find that vector, so that's going to be 2, 3, 3, and the vector from A to C, any point C, that's going to be the C vector there, is going to be 4, negative 3, 2, and if we go ahead and substitute those values into our parametric form of the plane, our general parametric form, we come out with the specific equation, parametric form of the equation of that particular plane, which is going to be described by those 3 points. Okay, now that is the parametric form of the plane. What we also want to do is we want to take a look at what's called the vector form of the plane. Now the vector form of the plane is going to look like this. It's r times it by n equals d. Okay, now we need to go ahead and talk a little bit more about this particular form later in class because it does get a little bit complicated. But let's just go through an example to make sure that we know how to get it. How to get a particular equation of a plane in vector form. So now the thing is, we have to go ahead and determine, okay, well, what is n? You know, remember what we said, n is actually going to be a normal vector. Well, which vectors are we choosing? The normal vector is actually going to be the vectors that is going to be described, that is going to be generated by the 2 vectors, basis vectors that we've used in the plane itself. So what that means then is that I have to use this vector and that vector, and I have to find the vector product of that. So if I go ahead and use my determinant method to go ahead and find out what that normal vector is, it comes up to 15, 8, negative 18 for this particular situation. So what I'm going to do then is I'm going to say, well, okay, here's the 15, 8, and the 18 because that's the normal vector. What is r? Well, r is just going to be a point, or the resultant vector, to any particular point on the plane. And we already have one of those points because we know that this point is actually on the plane as well. So we can just go ahead and use 1, 2, 3, dot that with 15, 8, negative 18, and we come up with negative 23. So what I have then is that if I go ahead and say that the resultant vector, if I dot that with 15, 8, negative 18, and I come up with negative 23, I found out the specific vector form of the plane described by those 3 points. Okay, now that's the vector form of the plane and the parametric form of the plane. What we need to do is we need to take a look at the Cartesian form of a plane. Now, the thing is if we go ahead and take a look at this particular vector form of a plane, we'll start off with this one here because this is a specific equation. We also know that the resultant vector is any x, y, and z that is actually in the plane. So therefore, if I go ahead and just write this as x, y, z, dot that with 15, 8, negative 18, which is the normal vector of the plane, equaling negative 23, because that's what our specific equation says. And if I go ahead and use the dot product this time, I'll come up with 15x plus 8y minus 18z is equal to negative 23. And there you go. There is the Cartesian form of the plane. So in its most general form then, we have ax plus by plus cz is equal to d, where a, b, c, and d are parameters and are real numbers. Okay, so that's quite a bit for us to take in, but it's going to be important that we also have a conceptual understanding, and let's kind of just wrap things up. Remember what we said when we talked about the 2-dimensional case? We can go ahead and represent any particular point in the 2 dimensions using a column vector. If we extend that same principle to the 3-dimensional case, then what we need to do is we just need to make sure to actually start from a point from the origin, go to a point on the plane, and then add all of those linear combinations which make up the plane. So therefore we can then come up with the parametric form of the equation. Now when we go ahead and take a look at the vector form of a plane, which is a little bit more complicated, it's going to be r, or the resultant vector, times it by the normal vector of the plane, equaling to a constant d. So long as we can find out what the normal vector is, as well as what that constant is, then we can find a specific vector form of a plane. If we go ahead from the vector form of a plane, substitute the resultant vector with x, y, and z, because we know x, y, and z represents any particular point on the plane, then we can go ahead and write the Cartesian form of a plane, which has this specific form for this particular example, and the general form that looks like that. Now, one of the things that's going to be very important as well is that we need to be able to transfer between one and the other forms for a plane. So let's see how you do, and we'll take any questions the next time that we see each other in class. Okay, bye.